For today's quiz, I built this wooden apparatus, and it's going to allow this mass that has an axis going right through the center of its rotation to travel down it. Now, this is a very heavy mass, and this rod is rather small. Our question is, how fast will this go down the ramp? Here's what your quiz looks like today. I'll hold that up right now. As always, mark your answers completely as possible and list your level of confidence. Typical student responses are that A, it's going to fall at gravity. Most of the time they'll be able to self-correct and say, well, it's at a ramp and we've seen things go down a ramp. It's not the same thing as falling. Others will say, well, because it's going down at an angle, it'd be some fraction of gravity. Some might say maybe like half of gravity or a third of gravity or something like that. But most students will end up saying that it's going to be a significant fraction of gravity because they've seen these roll down. So that's our typical responses that we get. All right, let's see if we can go through this problem. Now, remember, the purpose of these quick quizzes is to elicit dialogue. We want our students to think through the multitude of different ways of solving these problems. We want them to be creative and still understand the canonical ways of solving problems in physics. But in this problem, our students most likely will end up saying energy might be the easiest way to solve this problem. I agree. So let's do that. Let's solve an energy problem. Energy before equaling energy after. I'll just divide it into the before and after picture, and we know that up here it's got some kind of height, and we can put numbers in afterwards, and we'll choose really simple numbers, and if we'd like, we can measure what we actually have. One of the other things we need to keep in mind is not a lot of teachers have the ability to build an apparatus like this, nor the time, nor the space, so maybe they can use ours. So for right now, let's just use variables. Let's say this is going to have some mass m. That little caret symbol or apostrophe means after. And let's say that this is going to end up having some small radius right here. And I'll call that little r. And then I'll have this larger radius right here. And that will be capital R. And I'll do that for the other side also. And I'll put a capital R there. Now we know that we have a height, and the height we're going to go from center of mass to center of mass. So I can put something like this height to this height, and say, right there I have a certain amount of height that it's going to end up dropping. So we have potential energy. It's going to be going somewhere at the bottom, and it's also going to be rotating. So we have both kinetic energy and rotational energy. Let me put those in right now. Energy before equals our energy after, and we're going to end up having potential energy equaling our kinetic energy plus our rotational energy. So we have two types. Not only is it going to be rolling, but it's also going to be going somewhere. And here I can put my mgh equals my 1/2 my mv squared. That's how fast it's going to be going somewhere. And we're also going to have our 1/2 I omega squared. We're going to end up making some assumptions here. One of those assumptions is that the little tiny rod is really not going to add very much inertia where the big disc is. Now, it wasn't exactly a disc. I had to use some rubber stoppers to put that together, and I'll explain some of the problems that we had before. But let's consider this a disc. We could say where I is equal to 1/2 the mass radius squared, and now this is the tricky part. A lot of students will end up seeing, oh, R is what we're supposed to use, that small r, because I saw it on a formula sheet. But where is all of our inertia coming from? It's not coming from that little rod, it's coming from that big disc. That is where we want to be really careful with our r's. This would actually be our R capital. You know, you could use this small r and say it has a little bit of inertia. to compare the inertia of that big disk to that tiny one, it's not even going to be close. In fact, we might even say, just to make our life easy, we could say big R is equal to 10 times little r. So we've got a huge amount of mass and a large radius on that big disk, small amount of mass and a small radius on that rod. Let's consider it insignificant for this problem. So I can end up writing mgh equals 1/2 mv squared plus 1/2 our mass, our capital R squared, and then omega squared. But we want to end up finding how fast it's going. So let's look at the velocity down at the bottom of the ramp. I want to talk about v. How fast is it going? And a lot of our students think it's going to go pretty quick. If it's falling at gravity or half of gravity or even a third of gravity, by the time it gets down there, it's going to be going pretty quickly. We need to make this omega into a v so the v's can speak to one another so we can get an overall velocity at the bottom. A lot of our students have indicated they think it's going to be going pretty quick. So we can relate our velocity in a straight line to rotation through radius. And which radius is actually going to be in contact with that board to translate somewhere? It's not the big R. That disc doesn't touch. It's that little rod, that small r. So I'll say where velocity tangential equals r omega, or we could say omega equals velocity all over radius. And notice I'm using this small r here. Now, it's a squared term, so I've got to square this side, this side, this side. So maybe I can put squared, squared, squared. Put that in, and now I have my mgh equals my 1/2 mv squared. Let's take care of the 1/2 times 1/2. That's going to be 1 all over 4. I've got my mass, because the mass is the same. And I really should put afters on each of these. So let me put after. Now look, all of these are going to go away, as we're about to see in a second here. But I can say my r squared, capital R squared, and here I've got my velocity squared all over, and I'm going to put this right here, r squared. Now, you'll notice that I've got masses on the before and after picture, but they're all the same. So I can say where mass before and mass after are equal. So in other words, that mass and that mass and that mass, in other words, I'm dividing both sides by m on the bottom. Get rid of that mass, get rid of that mass. Mass goes away, which is really interesting. All right, so now I've got my GH, which equals 1/2 v squared plus, now notice I've got 1/4 here, and then I've got r, and I'm going to invoke this right here. I'm going to say, since our big R, and we're just making that number up, I can actually measure them, but it's a really easy number to work with. I can end up saying 1/4, and I'll put like a little star here to indicate where I'm getting that from. Put a little star right there. I can say big R is also known as 10r, and I need to square that all over r squared, v squared. Now, 10 squared is 100. So let me go ahead and do this. GH equals 1/2 v squared plus 1/4 100, and that's going to be r squared all over r squared. They cross out, v squared. It's getting hard to write as I go lower here. A little bit messy here, but 100 over 4 is simply going to be 100, like a dollar, 100 cents divided by 4 would be 25 cents. So let's put that on. So I've got my GH equals, I'll write this down just a little bit lower here, try to keep it a little neater, equals 1/2 v squared plus 100 divided by 4 is 25, and that would be v squared. So now I've got 1/2 plus 25. That's 25.5. So let's go ahead and put that together. GH equals 25.5 V squared. V squared would equal to our GH divided by 25.5. Square root both sides. Let's just put in some really easy numbers here. And notice I don't need to know the overall radius right now. I can simply use that ratio that I had. Let's just say that the height is following. Let's use a super easy number. Let's use 10 centimeters, 0.1. So I'll put it right here, 0.1 meters. So now I can end up saying 9.8 times my 0.1. So square root 9.8 meters per second squared times 0.1 meters, all divided by 25.5 equals my V. All right, I repositioned the camera because I wasn't sure if you could see it. I'll bring this back up here and then I'll just simply rewrite it. Our V is going to be equal to the square root of 9.8 meters per second squared times 0.1 meters, all divvied up by our 25.5. All right, so let's make our numbers even easier. Instead of 9.8, let's just call it 10. Because if we did that, then we could say 10 times a tenth is just 1. And so I would end up having that over 25.5. Let's ignore that 0.5. Let's just make our life easy. So I would end up having, let's just call it 25. So V would be equal to the square root of 1 meter squared all over second squared all over 25. Because 1 over 25 is, well, 4 times 25 is 100. So it'd be 0.04. So if I ended up just saying that I have the square root of 0.04, so, oh, I'm already down here again. Velocity equals the square root of 0.04, that would be meters squared seconds squared. The velocity would end up being 0.2, I think. Let me just double check. 0.04, square root that, 0.2 it is. So 0.2 meters per second, all right? That is a very, very, very small velocity. Nowhere even near a mile an hour, probably closer to a half a mile an hour. So this thing's going to be going very, very slow. Let's go back and see. All right, let's see if we can position this on here. And I'll try to get this straight. Try my best. Try my best. And that looks decent. And I'll let it go. Very, very, very slow going down here. The very bottom, it's going extraordinarily slow. And then it's going to work its way back up. All right, that was pretty extraordinary. How slow that apparatus worked its way down. Now, some of you are probably saying, that was such a short clip and all this work. Yeah, that's the carrot. That's the carrot. This is how teachers can help their students develop their physics ability, learning how to use the equations and mathematics appropriately, learning how to define and operationalize what we mean by radius, because that makes a big difference. Teachers, you need to do things of this nature. And if you can't, make sure you play this video. Students love this. They get to this point here after they invested and they made a claim. They thought it was going to go way faster. Their equations say, no, it's going to go way slower. And then we go back and they're like, oh my, it really did go extraordinarily slowly. So one of the other things that we end up doing here at the Idealized Science Institute is pushing long-term projects. This could be the beginning of a long-term. In other words, they saw something very interesting. Could they take it to the extreme? In fact, could we make this go slower and slower and slower? And let me just show you a few ways that students might go about this. It's still going to take some work, but they might say, what would make this apparatus even slower? They might say, well, it had something to do with the R values. Maybe they could make a claim and say, what if I had the R difference being even larger? they might make the claim as large R increases, our velocity at the bottom might decrease. That could be a long term. That could lead in. How are you actually going to do this? How are you going to make it bigger? Does mass matter? What should I do about the shape? Look, I had this 1/2 here because it was a disc. Are there other ways to decrease that 1/2? Make it more a hoop shape. And if it's a hoop, how does it connect? These are all things that your students could use as a seed idea to start engaging in long-term projects. We hope to have more and more videos that will help you on that, but either way, pretty neat problem. And that is your quiz for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.